Welcome back. Today we will continue our discussion on types. Briefly, here is our agenda. We will look at what is type checking, we'll look at what is type inference, we'll look at how equality of types can be compared and formalized, and then we will also look at polymorphism, which extends our discussion on type checking, and then we'll look at a couple of different variants of polymorphism itself. Right? Okay. So we all have encountered type checkers in some form or another while coding. Type checkers are the ones that tell you, hey, your code is incorrect because the types of these two variables don't match or these two expressions don't match. Right? Essentially, type checkers are trying to answer the question if a specified type and an actual type that is expecting is the same. This also extends to parameters, where the type of parameters must be equivalent of the actual parameters must be equivalent to the formal parameters, meaning the caller and the callee must match types for their parameters. Here is a simple example. Here you have a function f which takes in a value of type integer and it returns another value of type integer. Essentially, it multiplies x by 2. Now, if you have another value y which is of type string, then assign it to string. And if you try to assign z, which is an integer, with the value of f called with y, you would get a type error. Why? Because the expected value of y here, the formal parameter, is integer, but the type of the actual parameter is string, so hey, we have a problem. Right? Some languages go a bit beyond type checking to do type inference. Essentially, this means that the language tries to determine whether your code type checks without any type annotation or minimal requirement for type annotations. Right? We look at an example of how typing rules are used to infer types, but here again is the same example where you don't have any actual annotation of what the type of x, y, or z are, but the language is still able to detect that f of y is an invalid call because the value of the type of y and the expected type of the first parameter of ff do not match. Right? Here is an example of how type inference would be applied. Let's look at an example over here with two lines of code. The first line is defining a function f of x, which returns the tuple x comma x. Then the next line of code is essentially trying to apply f on 2, on the value 2, and then assigning to y. Right? Let's assume that here we are trying to infer the type of y. So first, we would assign pseudo types or unknown types to each of the variables here, including the function. So x would be assigned the type alpha. And of course, the return type would be alpha cross alpha because we know it's returning the tuple x comma x, right? And now let's assume we know nothing about how the function is defined itself. So we would simply define the function as type beta arrow gamma. Essentially, it means that it takes in parameters of type beta and returns gamma, right? Now, the type that we are essentially assigning meta variables to each of these types and trying to infer the values of these meta variables by applying the rule one on top of the other, right? So we'll assign the type delta over d to sigma to y, and then the type of f we know is beta arrow gamma, so we just leave it as it is. We just assign it to the same type, but we know that the value of 2 or the type of 2 is integer, so this is the first time we'll assign a concrete type to any of the variables here. Now let's look at the function application rule, which we saw before. Here it's the function application rule states that if your function goes from type 1 to type 2 and the type of a is type 1, then applying f on a gives you type 2, right? Now we know the value of a, which is int here, so we can go from there. So the first step is we replace every instance of alpha with beta because we know that to be true. So, and then we can replace gamma with alpha cross alpha because we know that also to be true from the return type of the function. Now we can infer that the type of f is alpha arrow alpha cross alpha, right? But we also, which means that the type of y, the type of value y is also the same as the function, because we are essentially y contains the value of whatever f returns by applying it on 2. But since we know the type of alpha here to be int in this specific case, we know that the type of y would be int arrow int cross int. So this is a simple example of how type inference works behind the scenes. Of course, in real life scenarios, type inferences are much more complex and with much more rules, right? Okay, another example of type inference is here with C++, which performs a local type inference, meaning let's look at a code here. My type, my var is something else. So my var is of type my type, and then if we try to assign v with f of my var, C++ automatically types v to t to whatever the return type of f is, because let's assume the type of f is type 1 arrow type 2. C++ will automatically type v to t2, so that the inferencing can be utilized later to perform optimizations. Another important thing to look at is types can also have names, name types. Here, for example, you're defining a type struct which contains two values, x and y, and then this whole type def is called coordinate. Now the internal types would be named c.x and c.y. Why is that relevant? To perform type equality. So let's extend the same example as before with another struct, but this time without names, which contain two values, int x and int y, and then there's a variable of this new struct called c2. Now, should c and c2 type check? Well, this depends on whether your language does nominal equality or structural equality. Meaning structurally, these c and c2 are the same type. They contain two integers called x and y, but nominally they are not equal. Well, we'll look at how these are done in the next slides. So nominal type equality simply checks for the names of the types. What is important here to note is that there is a difference between internal naming and the macro we use as a programmer. Here there are two type def structs which have the same name t, and it has one integer x, right? But they are defined at different points in the program, which is something that you can do in C, right? So the first, let's say you encounter the first, your program or your compiler encounters the first type def struct. There is a variable a of type t and variable b of type t, and a and b, of course, are of the same type. Now we have again introduced a new type t with the same structure, but this would still, a and c would not type check because internally there is a different naming that C uses for the first type t and the second type t, and these are not. So essentially the names, the internal names do not match, so the values are not of the same type. But some languages, for example like Modular 3, do something a little bit smarter, which is structural type equality. What this means is that it recursively checks whether the structure of your types, structure of your data are the same. Here is an example. You have a type t1a, which is a record, and it contains one integer. Type t1b is also a record, which contains one integer a, right? Type t2a is a record, which contains one integer and one other value of type t1a, which in turn recursively contains an integer. Type t2b is a record, which contains value of type integer, and then internally it also contains another value of t1b, which is structurally the same as t1a in that it contains one integer. So any variable of type t2a and t2b would be equivalent, would be the same type, right? Which means your type checker would pass, your type checker would say, hey, if you have a variable, I don't know, a1 of type t2a and a2 of type t2b, a1 equal to a2 would type check. So this is the notion of structural type equality which some languages perform, right? Another concept that we need to look at is polymorphism and how it relates to the type checking that we saw before. But before we look into polymorphism, let's look at a motivating example. Here you have a function which takes in an integer and returns a boolean. And then you have a variable v, which is of type subrange integers, meaning this value v can contain only numbers from 0 to 10. Now, if I call f of v, should it type check or throw a typed error? Well, you can say that any variable of subrange type 0 to 10 would be able to perform, or should be able to perform, the same computations as what you would be able to perform on an integer. But this leads us with a notion of polymorphism, which is essentially adapting a program feature to different type variations. So you saw a variable v, which is a variation of the integer type, which is essentially a subrange int type. Now, polymorphism is supported in different forms, 3 different forms to be specific. Ad hoc type of polymorphism, which is done either using overloading or implicit coercions. Then there is subtyping and parametric polymorphism. We'll look at each of them in the session one after the other. So first one is ad hoc polymorphism. Ad hoc polymorphism is supported in 2 forms, either overloading or implicit coercions. Right? To understand overloading, let's look at a couple of functions or a couple of variants of p. And here p is said to be overloaded for the type, for the parameter int, and then for the parameter float. It behaves differently. One prints int plus I, the other prints float plus the parameter. So here p is overloaded, meaning the function p is adapting to different type variations, right? P of, when you call p with value 1, it calls the first variant. When you call p with 3.14, it calls the second variant. So which method is called is decided at compile time. Just like methods and functions can be overloaded, operators can themselves be implicitly overloaded. Here, for example, if I replace I with I plus 1, still my program would type check because the operation plus is overloaded. Internally, integer addition would be an operation where, of type int cross int to int, meaning if I have an int cross int, which is I is an int, 1 is an int, it would again type infer the type as an integer, which means my overall method p, which needs to be called for the int variant, will type check, right? So I will have no problem there. The other variant of ad hoc polymorphism is implicit coercion, meaning you as a writer of the program don't specify how your values or functions need to be adapted to different type variants. Your language does it for you implicitly, right? Here is an example. You have an unsigned long v and an unsigned car c, and if you try to assign c to v, it would implicitly convert your c to a long, and then it would type check. The other variant, another example here, if you say float f equal to v star 3.14, even though v is of type long, it would be implicitly coerced to the type float, and then the overall computation will be able to occur without any problems, right? So we have looked at different variants of ad hoc polymorphism. Let's look at parametric polymorphism. Here you have an example in Scala, where you have redefined, or we have redefined, the function pair for strings and floats. This can be considered this can be considered overloading, but as you can see, this is still pointless duplication because essentially the code is doing the same thing. You have a defined pair which takes in an integer which returns the same integer as a tuple. You have the variant of pair with strings, which defines the same string as a tuple. You have defined float as the same float as a tuple, right? What languages like Scala provides is to parameterize the type itself. So how languages like Scala mitigate this is by using typed parameters, meaning let's look at the same function called pair from before, but instead of having a definition each for int, float, and string, it would have one definition which would take a parameter of type A. We don't know what A is yet, and then it would essentially, the first parameter expected is x of type A, and then it would return a variable of type A cross A, and then the computation would simply be returning the tuple, which is constructed using the value x, right? How you would call this is by saying pair, and you as a developer you can say I want to bind a with the type int and then pass the value 1 which is of type int, right? Same with pair of string, pair of float, and so on and so forth. As you can see, such parametric polymorphism reduces redundancy. Languages like Scala support such kind of parametric polymorphism, and of course these are also supported in other forms as templates and generics in other languages, right? Okay, now let's look at a kind of nitty-gritty of typed parameters as we saw before, right? What happens if you define type parameters scoped within each other? So here is an example. You're defining a function quad which takes in two type parameters a and b, and it takes two parameters, one of type a, one of type b. It returns a tuple of tuples. The first tuple is of type a comma a, the second tuple is of type b comma b. But this function quad reuses the definition pair. Essentially what this function is trying to do is it's trying to create two pairs. So it's redefining pair which takes in a value of type c. It takes a parameter z of type c, and then it returns the tuple z comma z, right, of type c comma c. And then the overall function returns two pairs, which calls where the first entry of the tuple would be pair of type a from the top definition with the value x, and then the second entry would be pair b with the value y, right? Let's the example that we saw before leaves us with the motivation that we need to introduce notation, right? So we are going to introduce notation so that we can formalize how to describe type parameters, as many languages have their own ways of dealing with these things, right? So Scala provides is nested scope type parameters in the way that I described here, but some other language might provide it another way. So how we formalize it is primarily using the for all notation. Essentially the type of pair is for all alpha, right? For any alpha, it could be integers, strings, I don't know, student type, whatever, right? It could be any type. For any alpha, the type of pair is alpha goes to, or alpha arrow, alpha cross alpha. The type of quad is for all alpha comma beta. The type of quad is alpha cross beta, arrow, alpha cross beta, right? So the typing rule, as we saw before, would also be adapted to include the for all notation, right? So you use the for all notation when you want to describe typed parameters. So here your function would be for all alpha if it's of type t, then f of t would be of type alpha arrow t or over the type t. Now let's formalize all of this a little bit, right? So if you have a function f, which is defined as for all alpha tau, tau is here essentially the type of your function itself. It can be anything. F, when it is parameterized with the type t, would essentially be the substitution of alpha with t. So you're saying essentially substitute alpha with t, and the type of the function is essentially the rest as is, which is tau, right? It can be here in this case, alpha goes to alpha cross alpha for pair, and alpha cross beta, or alpha cross beta goes to alpha cross alpha star beta cross beta, right? So, and this would be sufficient for any of the type checking. There is of course a lot of complexities which we will not go into because of the scope of this lecture itself, but I hope I have triggered some juices here for you to look into books on type theory for the same, right? Okay, so let's use the principles that we have learned for parametric polymorphism and typing to apply it on the function and the value that we saw before and how they would be input, right? So here you have a function f which takes in a value x and returns the tuple x comma f. The The only thing you will have to do is, if f is parameterized by type, you would have to include the for all notation. It's very clear, right? But when you want to apply to a variant of f, you can simply, as I showed you before, replace alpha with, for example, alpha 1 here. Alpha 1 would be integer in the variant of val y equal to f of 2, and alpha 2, or you can replace alpha with alpha 2. You can remove the for all notation, and then alpha 2 would here refer to string because of your function calling foo with string here, right? Okay. Now, before we look at the other kind of polymorphism, of subtyping polymorphism, I need to introduce briefly what object orientation is. Most of you might already know about this, but let me briefly introduce object orientation. A language is supposed to be object oriented if it supports the three concepts that I've described here: subtyping, inheritance, and dynamic dispatch. We will look at each of them briefly in the next slides. But essentially, subtyping allows you to say that a type, for example here cat, is a subtype of another supertype animal, right? What this means is that every time for a particular operation an animal is requested, you can easily pass in a cat, right? Let's say I'm constructing a list of animals. I can always get an object of type cat and add it to this list, right? Barring some constraints. Inheritance essentially says that whatever property my supertype has, or whatever the property of interest is, I can inherit. For example, if animal has a way it computes age or speed of the animal itself, this means that I know how to compute the same property for a cat. Dynamic dispatch, on the other hand, allows you to dynamically modify select behaviors, right? So maybe animals yell in a certain way or speak in a certain way, but a cat meows. So that's a variant of dynamic variant of the behavior, right? We look at each of these properties, right? Inheritance, subtyping doesn't require too much description other than the formalisms, which I'll go into in the next slides. But inheritance, for example, is simply, as I mentioned before, that if you have a way to compute the age of an animal, subtypes of animals, be it cat or cow, can inherit that behavior, and they also know how to implicitly. Objects of type cat and objects of type cow have their own way of, or can inherit the way age is computed, right? Formally, subtyping uses the notation less than semicolon, less than colon. So essentially what this means is that type T1 is a subtype of the supertype T2. Subtyping generally means, generally when you say T1 is a subtype of T2, which it means that it's transitive. Meaning if T1 is a subtype of T2 and T2 is a subtype of T3, it means that T1 is a subtype of T3. And they are antisymmetric, meaning that if T1 is a subtype of T2 and T2 is a subtype of T1, it means that T1 and T2 are the same type. This is sometimes used to define type equality in type systems simply by saying that T1 has to be a subtype of T2 and T2 has to be a subtype of T1, right? Some languages have the notion of a topmost type. For example, Java, which has the object type, which is the supertype of every other type, right? So java.lang.object is not a subtype of any type, right? Here is an example of different subtypes in the world of integers. Integer here is a supertype. The type of subranges 0 to 20 is a subtype of integers. The type of subranges 0 to 4 and 10 to 20 are subtypes of 0 to 20, and so on and so forth, right? This is just to give you a visualization of how subtypes can look like in practice. Type safety here also means that if a property P is ensured for T1 and T2 is a subtype of T1, then this means that the same property P of T2 is true, right? So essentially what this means is that any property P of interest is inherited by all of its subtypes, right? Here is an example. Let's look to understand whether we have understood type safety or not. Here is the example is in a Pascal-like language. You have a function f. function g, which takes in a function f that takes in a value of range of type 0 to 10 and returns a type 0 to 10, and the overall function g returns a type value of type 0 to 20, value in the range 0 to 20, right? You have two variables of type x and y which are in the range of 0 to 10, right? And then what this essentially does is that it adds the computations of performing f on the value 0 and f on the value 10, and then it adds both of them and returns the value, right? Now the question, and of course there are a couple of more functions, h1, which takes in a value x of type 0 to 10 or range 0 to 10 and returns a value of type 0 to 3, h2, which takes in 0 to 3 and returns a value of type 0 to 10, right? Now the question, is g of h1 type safe? Well, it is type safe because the return value of type h1 is within the range 0 to 3, which is a subtype of 0 to 10, which is what is expected, meaning v0 and v10 can safely store the return value of h1, right? Because both of them are expecting values between 0 to 10, so it is type safe. If is g of h2 type safe? Well, not, because h2 takes in a value takes in a parameter of type 0 to 3, which means it cannot accept the value 10. The g, for example, has a value g, for example, has a call to f which contains the value 10. It cannot accept it, so it is not type safe. So how you formally define this is using the arrow rule. What the arrow rule essentially tries to say is that a function of type t1 arrow sigma 1 is a subtype of t1 arrows sigma 1. I think it's t2 arrow sigma 2. I'm really sorry. I need to correct this. Only if the parameters are supertypes and the return values are subtype. How it is represented formally is that if t1 is a supertype of t2 and sigma 1 is a subtype of sigma 2, right? Here the parameters are represented by sigma, and then the parameters are represented by t1 and t2, and then the return values are represented by sigma 1 and sigma 2, right? So if t1 is a supertype of t2 and sigma 1 is a subtype of sigma 2, then the function of type t1 arrow sigma 1 is a subtype of t2 arrow sigma 2, right? If you go back to the previous example and apply this arrow rule, you can formally understand why g of h1 type checks and g of h2 does not type check, right? So now let's finally look at dynamic dispatch. As I mentioned before, dynamic dispatch is a way for you, for your type system to know which particular variant of a method needs to be called depending on, so let's say your animal has, your class animal or your type animal has a function doit, and you have subtypes cow and cat. Each of them have their own variants of doit, right? Let's look at it practically with an example from Java and how it's accomplished. Here you have a class or type animal which has age, and then it initializes the age to 0 in the constructor. Then it has a function getAge which returns the age, and then it has a function do, right? Now you have a function makeDo which calls t.do, which takes in a parameter of type t and it performs t.do. What happens here depends on what is passed, right? So to extend the type animal, you have a subtype cat of the supertype animal which has its own variant of do, which simply mews. A variant of dog, a subtype variant dog of the supertype animal performs the same do, but it just wags its tail, right? So now the question is, what would make do do? What would make do do, right? This depends on how do is called. Here, if you call do with a new cat or a new dog, it dynamically dispatches the variant of the method do based on what object is initialized, right? So I will not go into the depths of how dynamic dispatch is implemented, but to understand the notion of how dynamic dispatch can be implemented, we need to understand what the static type is and the dynamic type is, right? If you look at the code above, animal A equal to new cat, the type of A without executing the code would be animal, right? So the static type of A is animal. But the dynamic type, which is stored in the heap of the same variable A, would be cat, and it would have its own variants of the do method and every other thing, which means when you call a.do, the dynamic type is then looked up, and then it invokes the variant of do that is called by do here, right? So essentially we have come to the end of our discussion on types. Today in this session we looked at briefly what is type checking, we looked at what is type inference, and then we also looked at how program features can adapt to type variances, aka polymorphism. We saw 3 different types of polymorphism. Thank you.